So let us start our lecture on autoencoders and PCA. These are algorithms for learning low-dimensional representations of high-dimensional data, or manifold learning algorithms. We start with the shallow learning formulation and specifically a linear formulation of the problem. Let us first make some definitions. We call our data set capital X. This is a matrix with capital T components or rows and n dimensions. We here use capital T for counting the number of data points or rows in order to avoid confusion with little n, but also because later we will speak about time series and then the row index becomes a time index. In the current lecture, there is no particular ordering or time. It's just, so T is just an index. The individual rows of this matrix are vectorized data, and that could be anything from measurements, a vectorized image, an audio signal, or whatever we want. In order to simplify some of our derivations in the next couple of slides, we will assume that this data is empirically mean-free. So that means if you just sum the data over the rows, then you obtain the zero vector. If that is not the case in the initial data, we just compute this empirical mean and then remove it. And we will also store it for later use, because if we remove it, we want to be able to put it back later. Here is the formulation of the linear dimension reduction problem. We want to find vectors W on which we can project our data X. So that means we take every row vector of X, every data point of X, and we compute the scalar product with the vector W. And the result of the scalar product is a number or a scalar for every data point. And that means the result for all the data points is again a vector Y, which has the number of total data elements as a size. So it has capital T as length. And we want to find W such that this projection is in some sense optimal. And we will look at different optimality criteria. So this is a definition of a one-dimensional projection, or a projection to a one-dimensional subspace, because we have used only one vector W here. We can generalize this concept by using multiple W vectors. So then we define a projection matrix, which has as a format or as a shape the number of data dimensions n and the number of vectors m that we consider. This defines a m-dimensional linear subspace if we multiply the data matrix X with the projection matrix W. Usually we consider a situation where m is smaller than n, so we use less vectors W than we have dimensions in the original data, often much less, and in this case W performs a dimension reduction. Dimension reduction often means that we do a lossy compression. So we discard the information which is in some of the dimensions of the original data, and we only keep some of the original information, and therefore we lose some sort of information, and we want to minimize the information loss in some sense. So the aim now is, given data X, search a projection matrix W with this shape n times m, which projects the data onto a linear subspace by minimizing some loss or maximizing some score. What are meaningful loss functions here? In this lecture, we will consider two different kinds of losses for this problem. The first idea is to maximize the explained variance. So that means we want to maximize the variance of the data after projecting it. Since the data is mean-free by definition, we can just compute the variance as the square norm of the projected vector as shown here. So for a one-dimensional projection into a single vector W, where our projection is again a vector Y of the number, which has a length of the number of data points or samples. This is simply the sum over the squared elements of this vector. or we can write it as the squared Euclidean norm of the vector resulting from x times w. And we can generalize this norm to a matrix norm if w is not just a vector but a projection matrix. Alternatively, and it is perhaps a little easier to see why that is meaningful, we want to minimize the reconstruction error. So the idea of the reconstruction error is to say we project on our low-dimensional subspace and then we have some method of lifting back, of going back from the low-dimensional subspace to our full-dimensional space, and then we compare to the original data points, and we want to minimize the difference between those. We want to minimize the reconstruction error between the projected and lifted data and the original data. Here we will use matrices, we will use special matrices W with orthogonal vectors, and we will look into that more closely. And in this case, we can write the projection and the lifting as WW transposed. So W, the application of W to X, projects the data down, and then the application of W transposed to the result lifts the data back on the original space. And therefore we can look at the difference between the X matrix and XWW transposed. This is again a matrix of errors which has the same shape as X, so it's number of data points times number of dimensions in the high dimensional space. And then we can use, for example, the Frobenius norm, so the sum of the squares of all elements, in order to measure the error. So this is the reconstruction error, and we want to minimize that. The method that optimizes these linear dimension reduction problems and actually simultaneously optimizes both loss functions, so we will be able to show that these are equivalent in the formulation we just made, that is the principal component analysis, or PCA. And here you see PCA in action, so consider we have the two-dimensional data shown by the dots here. And what PCA does is now to find a new basis for the data. So first of all, it moves the center of the data, so that is removing the arithmetic mean, which we have done in the very beginning of the slides. And then we find projection directions W, in this case W1 and W2, indicated by the blue and the red arrows, which are chosen such that both the reconstruction error is minimal if we choose these directions, and the explained variance, or the variance after projection, is maximal. Of course, since we only have two-dimensional data, it makes only sense to use these criteria to find the first vector, and then for the second vector we have to somehow define how to choose it. Because as long as these two vectors are not identical, any direction of the second vector would be okay for keeping all the information in the data set. We could always reconstruct the full information from two coordinates as long as these coordinates are not measuring the same thing. And in PCA, the convention is that these directions are orthogonal to each other. So the red vector is orthogonal to the blue vector. The blue vector is pointing into what's called the first principal component of the data. You can see that this is the direction that if you project the data on it, maximizes the variance along this projection. In other words, this is the direction along which the data has its largest extent or variance. On the other hand, it is also true that this is the direction with minimal reconstruction error. So if we are looking for a linear projection in this data set, in this two-dimensional data set, into one dimension, and then ask what is the reconstruction error. So what that means is you choose one direction, you project your two-dimensional data onto this one direction by choosing an orthogonal projection. So you go to the closest point on the one-dimensional subspace, and then you ask what is the difference or the distance between this position that I'm compressing my data to or projecting my data to and the original point. So what is the What is the distance I have had to move from the original point's location in 2D to its projection in the subspace? And in this example, this is just the distance of the point to the blue arrow in the direction of the red arrow. So if we project every point on the closest position along the blue arrow, so the first principal component, then of course we will make an error. We will lose the information about the orthogonal direction, the red direction, but amongst all linear subspaces, this is the best choice. This is where this error is minimal, this reconstruction error is minimal. But first we want to derive PCA using the maximum variance after projection argument. And we will look at the first principal component of a high-dimensional dataset first. So we are looking for one vector, W1, and we want to choose W1 such that amongst all vectors that we could choose, W1 is the vector where the projection variance, or the variance of the data after projection, is maximal. Of course, we have to add one constraint, namely that the norm of the vector W that we are searching for is normalized, is equal to 1. Because otherwise we could just maximize this quantity xw square norm by making the vector w longer, and that's not what we're interested in. That would be cheating. We want to find its optimal direction, so we have to cap its norm. As we discussed before, because the data is centered, is arithmetically mean-free, we can measure the variance of the projection by looking at the 2 norm of xw. So we maximize the 2 norm of xw over the vectors w that are normalized, that have unit norm. As a side remark, I'm speaking of maximizing 2 norms here. Really, in order to get the 2 norm, or this is actually the square 2 norm, what we would also need is we would need to divide by the number of components in the vector. That's something I'm not doing here. And the reason for that is simply when I'm maximizing, and when I'm looking for the argmax, this constant factor doesn't matter, so I'm simply ignoring that. Now the square 2 norm of xw is equal to the following vector product, wx transposed xw. Yeah, so here I've used that xw squared can be written as xw transposed times xw, and then I have exchanged the first 2 elements of xw transposed to w transposed x transposed. Now there's a different way of writing the same optimization problem. Instead of putting the norm of w being equal to 1 as a constraint to the optimization problem, we can include it in the loss function. So we maximize w transposed xw divided by w transposed w, which measures the square norm of w. So this is equivalent, but this is now a much easier formulation because now we don't have to worry how do we impose the constraint of w having unit norm during the optimization problem. We can just directly optimize this loss function, and then we will automatically avoid the problem that we can trivially maximize it by making w longer. Alright, so how do we maximize this explained variance over w? So first of all, we see that x transposed x is a matrix with the size of the number of dimensions in the data times number of dimensions in the data. So it's a square matrix, and we can compute it from the data x alone, and we can pre-compute it before doing any maximization. Also, x transposed x is a symmetric matrix, so it's a symmetric square matrix. And for this matrix, this score function here, w transposed of this matrix times w normalized with w transpose w, this is called the Rayleigh quotient. And the Rayleigh quotient is maximized by the w vector, which is the eigenvector corresponding to the largest eigenvalue of this matrix. Since this is a symmetric matrix, the eigenvectors and eigenvalues are real and they are the same as the singular vectors of the matrix. So we can either use an eigenvalue decomposition or a singular value decomposition of the matrix X transposed X in order to find W. Yeah, so we do an eigenvalue decomposition, for example, we compute the eigenvalues and eigenvectors, and then we take the eigenvector which has the largest eigenvalue, and this is our optimal W. So the optimization problem can be solved in one shot by applying a simple linear algebra operation. Alright, this gives us the first principal component. How do we proceed for further principal components? We have said that we want the other principal components to be orthogonal. So we want the second principal component to be orthogonal to the first principal component. We want the third principal component to be orthogonal on the plane spanned by the first two principal components, and so on. Conceptually, what we can do is the following. We have found the first principal component as described before by performing an eigenvalue decomposition and selecting the eigenvector with the largest eigenvalue. Now we take the data X and we remove the contribution from this first principal component. So that means we project our data onto the first principal component, we lift it back to be in the same space, and then we have our data matrix explained in the first principal component only. So that part of the data that can only be explained by the first principal component. And we remove this contribution, this first principal component contribution, from our data matrix. So we subtract it. What is left is the residual. So what is left is the part of the data that cannot be explained by the first principal component. And then we perform the same procedure again, so finding the optimal projection, the maximum singular component or the maximum principal component with the remaining data, with the residual data. In general, we do this with multiple principal components. So say we have found the first principal component, then we just remove the first. Say we have done that twice, so we have repeated finding the largest eigenvalue and eigenvector a second time. We remove the contribution of the second principal component from the data. Then we can also write this in one step by taking the data matrix and removing the summed contribution of all the principal components we have found so far. This is shown in this first equation here. And then we find the next principal component by again maximizing the Rayleigh coefficient with the matrix resulting from this remaining data, x hat. And so each time we do this, we get another principal component, and we have made sure that the principal components are orthogonal to each other by always removing the contribution of one principal component from the data. So whenever we do this, we are ensuring that the remaining data only lives in the orthogonal subspace. So we cannot find the same direction again. Now this construction is purely for the sake of the argument. In practice, we do not need to do this vector by vector, always removing the contribution of the last vectors and then performing an eigenvalue decomposition again, because by definition the eigenvalue decomposition of X transposed X will give us all the eigenvectors, and all these eigenvectors are orthogonal to each other. So in other words, we can find all principal components at once by performing a complete eigenvalue decomposition of X transposed X. In other words, the matrix W that we are looking for, the optimal projection matrix, is simply the matrix which diagonalizes the matrix X transposed X. And then we just choose, however many columns of W of the eigenvector matrix we want, because we need to decide how many dimensions we want to project the data onto, how much our dimension reduction should do.